Hi, welcome back to week 3 of Logic, Language and Information 2. In this lesson, I'm going to explain the rules for tree proofs for first-order predicate logic. This lesson will just contain the rules, so you might find yourself coming back to the lesson again and again until you're familiar with all of these rules and how they work. We'll start with a quick revision of the tree rules for propositional logic. If you need more help with these rules, take a look back at the resources we recommend in the subject notes, and especially the videos from Logic, Language and Information 1. Now, the tree rules show how you can develop formulas as we spell out the implications of each individual statement. The rule for a conjunction, for example, goes like this. We develop a conjunction A and B by writing down both of the conjuncts A and B, because after all, the A and B need to be true if A and B is true. A negated conjunction is different. We develop not A and B by writing down not A and not B in different branches. If not A and B is true, then the conjunction A and B is false, and this means that either A is false, so not A is true, that's the left branch, or B is false, so not B is true, and that's the right branch. These two possibilities are represented in the two different branches. A disjunction works kind of like the negated conjunction works. If the disjunction A or B is true, then either in one case A is true, or in another case B is true. These two possibilities are again represented in two different branches. A negated disjunction, on the other hand, doesn't branch. If not A or B is true, that means that A or B is false, which means that both A and B are false, which means that not A and not B are both true. A conditional, if a conditional A implies B is true, then either A is false or B is true. So we've got two branches, one with not A and the other with B. Conversely, for the negated conditional, if A implies B is false, that means that A is true and B is false. So we write down A and not B in the one branch. Now for a biconditional, the structure of this rule is slightly different. If and only if B is true, then A and B have the same truth values. It follows that either A and B are true, that's the left branch, or not A and not B are true, that's the right branch. So we've got two branches, one with A and B, and the other with not A and not B. The negated biconditional is similar. If and only if B is false, then A and B have got different truth values, and that means that either A is true and B is false, the left branch, or A is false and B is true, the right branch. Now, the rule for double negation is simple. If not A is true, then that means that A is true, because not A is false. Finally, we have the rule for closure. If a branch contains a formula and its negation, then that branch closes. The formulas in that branch can't all be true together, and we indicate that by putting an X under the branch. So these are the rules for propositional formulas. That's background knowledge. Now we'll look at the rules for quantifier formulas. We'll start with the rules for the existential quantifier formulas. If we have a formula starting with an existential quantifier, we process it by adding an instance of the formula involving a name new to the branch. Here's why this is the rule. If there's an object that satisfies condition A, that's what this says, it says something has property A, then we can give that object a name. But we cannot assume that any of the names that we're already using are suitable for the job. They may be naming other objects, but we can add a new name to our vocabulary to use to indicate the object satisfying condition A. So that's what we do. If an interpretation makes the existentially quantified formula something has property A true, then it will also make this instance true, where N is the new name. Now, for a negated existentially quantified formula, if we know that nothing satisfies condition A, that's what this says, it's not the case that there is something satisfying condition A, we know that whatever object we talk about doesn't satisfy that condition. So we're permitted to add the negated instance, it's not the case that object A has property A, for any name A that we like. And so this rule can be used again and again. If we learn of other objects like B or C or D or N or whatever, we can revisit this formula and derive other instances of the formula not A. Now, for the universal quantifier, its rule is straightforward. If every object satisfies condition A, then we can choose any name we like as an instance. This rule can be applied again and again as more names become available. None of the individual instances are enough to exhaust the meaning of the quantifier, the original formula, because the more objects we have in our interpretation, the more instances we need to derive. Because this says that everything has that property, so the more things we talk about, the more things that we can apply this fact to. The negated universal quantifier formula, though, is different. If we know that not everything has this property, we know that not every object satisfies this condition A. It follows that we can find some object that doesn't satisfy the condition. And we, again, can use a new name to pick out such an object. And not A applies to that new name N. This is the rule. From it's not the case that everything has property A, we derive an instance, not A, where X is substituted with a new name N, with the name N new to the branch. Now, this is not a rule for repeated use. Once we have one instance, that's enough to make the negated universally quantified formula true. If an object N doesn't satisfy the condition A, then indeed not everything satisfies the condition. And so that exhausts the meaning that we need to extract from this formula. Now, that completes the rules. Now, you'll notice that these rules come in two varieties. The existential quantifier and the negated universal quantifier rules are both what we call particular rules. You can use these rules once and then tick them off to indicate that they've been applied. These rules introduce a new name to the tree for a particular object, whereas the universal quantifier rule and the negated existential quantifier rule are what we call general rules. These rules can be used repeatedly. You don't use a tick when applying these rules. Rather, each time that the rule is applied, we use a backslash and write the name that we used in that instance of the rule to remind us of where that name got applied. But we could use those rules generally again and again to all of the objects in the domain. And now these are all the rules that we have. This completes the presentation of the rules for trees for first-order predicate logic. In the next lesson, we'll see how these rules are applied as you develop a tree and read off the results of a tree to show that an argument is valid if the tree closes, or to construct a model if the tree stays open.